Part 1: Introduction and the Andromeda Galaxy. Since time immemorial, humanity has directed its gaze toward the nocturnal firmament, captivated by that luminous smudge that cuts through the darkness like a silver wound in the fabric of the cosmos. The ancient Persians called it al-Sufi, the little cloud. Medieval Arab astronomers observed it with utter fascination, completely unaware that this faint luminescence contained over 1 trillion burning suns. For centuries, it remained an enigma suspended in the celestial vault, a mystery that defied full human comprehension. Today, armed with telescopes that penetrate the very depths of space-time, we know the definitive truth. Andromeda is not a mere gas cloud. It is a colossal galaxy, a cosmic titan hurtling toward us at a dizzying velocity. Prepare yourself for a journey that will profoundly transform your understanding of the universe, because today we will discover exactly how truly immense Andromeda is and what its inevitable collision with our own Milky Way will signify for the distant future of everything we currently know. On a crystal-clear night, far away from the light-polluting glow of major cities, you can observe the Andromeda Galaxy with your own unaided eyes. You do not require sophisticated telescopes or advanced astronomical equipment. Simply lift your gaze toward the constellation that bears its name, and there, like a diffuse smudge of light, lies our massive galactic neighbor. What you are contemplating in that precise moment is light that has traveled for 2.537 billion years across the interstellar void to finally reach your retina. These ancient photons began their journey when the first complex multicellular life forms were only just emerging on Earth, long before the dinosaurs ever walked across our planet. If you enjoy calmly navigating the profound mysteries of the universe, this space is absolutely for you. I invite you to subscribe to the Deep Space Calm and continue our joint exploration. Accompany each new cosmic voyage with tranquility and insatiable curiosity. And please tell me at the end, from what precise location in the world are you listening to us, and what time is it there? Andromeda, officially catalogued as M31 or NGC 224, is the closest major spiral galaxy to our Milky Way. It is situated at an approximate distance of 2.537 million light-years, which is equivalent to approximately 24 quintillion kilometers. To put this truly staggering figure into perspective, if you could travel at the speed of light, it would take you more than 2.5 million years just to reach it. If a commercial jet airliner, flying consistently at 900 kilometers per hour, were to undertake this journey, it would require 3 trillion years to complete the entire trip, an inconceivable amount of time, 200 times greater than the current calculated age of the universe. For countless centuries, astronomers debated the fundamental nature of Andromeda. In 1612, the German astronomer Simon Marius described it poetically as the light of a candle seen through a translucent horn. It was not until 1925 that the legendary Edwin Hubble, utilizing the 100-inch telescope at Mount Wilson, conclusively demonstrated that Andromeda was not a mere nebulosity within our galaxy, but an entirely separate stellar system. This monumental discovery completely revolutionized our understanding of the cosmos, instantly expanding the known universe by millions of light-years, and revealing that the Milky Way was just one among countless other magnificent galaxies scattered throughout space. The observation of Andromeda presents several truly fascinating characteristics. With an apparent magnitude of 3.4, it remains one of the most distant objects visible to the naked eye. Its angular size in the sky is remarkably large, approximately 3 degrees, which is equivalent to 6 times the full diameter of the Moon. However, we only perceive its bright, concentrated nucleus with our unaided eyes. If our visual capability could fully capture the entire true extent of Andromeda, including its faint outer halo, it would occupy an area of the sky 7 times larger than the full moon. It is a profound cosmic irony that one of the most massive and extensive objects in the local universe appears so incredibly diminutive when we gaze upon it from our vantage point here on Earth. The composition of the light we receive from Andromeda reveals deep secrets about its inherent nature. Modern spectrometers meticulously break this light down into its constituent components, allowing astronomers to precisely identify the chemical elements present in its stars. We find abundant hydrogen, helium, carbon, oxygen, iron, all the fundamental ingredients that form not only stars, but also, eventually, planets, and perhaps even complex life itself. The spectral analysis also unveiled something profoundly unsettling. Unlike the majority of distant galaxies we observe, whose light is shifted toward the red end of the spectrum due to the relentless expansion of the universe, the light from Andromeda exhibits a characteristic blue shift. This unequivocally signifies one single thing: Andromeda is not receding from us. It is drawing closer. Continuing our journey of profound discovery, we must ask, what exactly makes Andromeda so special in comparison to our own home galaxy? The Milky Way, our cosmic sanctuary, is a barred spiral galaxy that contains between 250 billion and 400 billion stars. Its diameter stretches approximately 100,000 light-years, an extent that light, traveling at 299,792 kilometers per second, requires 100 millennia to fully traverse. Our own solar system orbits the galactic center at a distance of about 26,000 light-years, completing one full revolution every 225 million years, a period dramatically known as the cosmic year. Andromeda, for its part, is also a spiral galaxy, although it conspicuously lacks the prominent bar structure that distinctly characterizes the Milky Way. Both colossal galaxies feature spectacular spiral arms, where vast amounts of gas and cosmic dust are concentrated, giving spectacular birth to new generations of brilliant stars. Both possess a dense central bulge, populated predominantly by ancient yellowish stars. Both harbor at their core a supermassive black hole, gravitational monsters millions of times the mass of our own Sun. Yet, the simple similarities end here, because in almost every measurable aspect, Andromeda truly overshadows the Milky Way in an impressive manner. The first profound indication of Andromeda's superiority lies in its sheer stellar population. While our galaxy contains up to 400 billion stars, Andromeda definitively harbors approximately 1 trillion suns. This means that Andromeda possesses between 2.5 and 4 times more stars than the Milky Way. Imagine for a moment the sheer magnitude of this figure. 1 trillion stars, each one potentially surrounded by planets, moons, and asteroids. The sheer quantity of worlds that could exist within Andromeda defies all existing human comprehension. If you dedicated a mere single second to contemplate every star in Andromeda, you would need more than 31,000 years to observe them all. The second crucial difference appears when we precisely measure the diameter of both galaxies. The Milky Way stretches about 100,000 light-years from end to end. Andromeda, in stark comparison, spans approximately 220,000 light-years in diameter, more than twice the size of our own galaxy. This dramatic difference becomes even more striking when we consider the area. Andromeda occupies a cosmic space approximately 5 times greater than the Milky Way. If we could place both galaxies side by side and observe them from a vast distance, the Milky Way would appear definitively as a younger sister next to its gigantic companion. However, an intriguing paradox exists when we thoroughly analyze the total mass of both galaxies. Despite being significantly larger and containing far more stars, Andromeda possesses a total mass of approximately 1.5 trillion solar masses, while recent meticulous studies suggest that the Milky Way might have a comparable or even slightly superior mass, possibly reaching up to 1.9 trillion solar masses. How is it possible for a smaller galaxy to be demonstrably more massive? The answer lies in the mysterious halo of dark matter that entirely surrounds each galaxy. Dark matter, that elusive and invisible substance that constitutes approximately 85% of all matter in the universe, forms massive, extended halos around galaxies. Apparently, the Milky Way possesses a more extensive and denser dark matter halo than Andromeda, thus compensating for the difference in visible stellar matter. Both galaxies form part of what astronomers call the local group, a collection of over 80 gravitationally bound galaxies that occupy a volume of approximately 10 million light-years in diameter. Within this group, the Milky Way and Andromeda are, by far, the two dominant members. The third largest galaxy, the Triangulum Galaxy, or M33, contains a mere 40 billion stars, 10 times less than our home galaxy. The rest are predominantly dwarf galaxies, satellites that meekly orbit around the two giants like planets orbiting stars. For many decades, astronomers assumed that Andromeda was the undisputed queen of the local group. Its larger diameter and its superior stellar population seemed to definitively confirm its cosmic dominance. However, more precise recent measurements of the galactic masses have revealed that Andromeda's reign might not be as absolute as previously thought. The Milky Way, our seemingly modest galaxy, could in reality be the more massive of the two. This startling discovery has compelled scientists to thoroughly reconsider the dynamics of the local group and the critical predictions about the future inevitable encounter between these two cosmic titans. The internal structure of Andromeda also presents several highly notable characteristics. Its galactic disk, where the majority of its stars, gas, and cosmic dust reside, has a thickness of approximately 1,000 light-years in the outer regions, thinning considerably compared to the dense central bulge. Andromeda's bulge extends about 10,000 light-years from the center, a densely populated region where the stars are so tightly packed that, if we lived there, the night sky would be permanently illuminated by thousands of brilliant stars, each one visible as a point of light comparable to Venus or Jupiter as viewed from Earth. The spiral arms of Andromeda, although perhaps less distinct than those of some other spiral galaxies, contain vast, complex clouds of molecular hydrogen, the magnificent stellar nurseries where stars are continuously born. Observations in infrared wavelengths reveal spectacular regions of intense stellar formation, where massive and hot stars illuminate the surrounding clouds, creating stunning emission nebulae. The stellar formation rate in Andromeda is approximately 1 solar mass per year, quite similar to that of the Milky Way. This means that every single year, sufficient gas condenses within Andromeda to form the equivalent of one star the size of our Sun. Surrounding Andromeda's visible disk extends a faint stellar halo, populated by globular clusters and stellar streams, the shattered remnants of dwarf galaxies that Andromeda has mercilessly devoured throughout its violent history. Astronomers have cataloged approximately 450 globular clusters orbiting Andromeda, significantly more than the 150 that orbit the Milky Way. These clusters, each containing hundreds of thousands of extremely ancient stars, act as invaluable cosmic fossils, preserving critical information about the earliest epochs of galactic formation. But perhaps the most truly intriguing aspect of this comparison lies in what is yet to come. Andromeda and the Milky Way are not merely cosmic neighbors coexisting peacefully in space. They are two colossal gladiators in a grand gravitational arena, inexorably approaching one another at a velocity of approximately 110 kilometers per second. At this very instant, as you are reading these words, Andromeda has drawn several hundred kilometers closer. Every second, every minute, every year, the vast distance separating us diminishes. The question is not if these two giant galaxies will collide. The crucial question is precisely what will happen when they eventually do. If we continue our journey into the distant future, we will discover that this cosmic collision will not be a sudden, catastrophic event, but rather a majestic cosmic ballet that will unfold over billions of years, completely transforming the entire structure of the local group and potentially determining the ultimate fate of billions of stellar systems, including, quite possibly, our very own. In 2012, utilizing the superior capabilities of the Hubble Space Telescope, astronomers measured the transverse, or side-to-side, motion of Andromeda across the sky with unprecedented precision. The meticulous measurements confirmed what many had long suspected. Andromeda is heading directly toward the Milky Way on a path set for a direct, inevitable impact. The James Webb Space Telescope, with its superior infrared capabilities, has enabled scientists to penetrate the dense clouds of dust that obscure parts of Andromeda, revealing previously hidden stellar populations. These advanced observations have refined our estimations regarding the age of different galactic regions. While the central bulge contains extremely ancient stars, with ages exceeding 10 billion years, the spectacular spiral arms show compelling evidence of recent and continuous stellar formation. Some stars in Andromeda are merely a few million years old, veritable cosmic infants compared to the universe's total age of 13.8 billion years. The rotation of Andromeda presents peculiar characteristics that have intensely intrigued astronomers for decades. Unlike a rigid disk that would spin uniformly, Andromeda exhibits differential rotation. The interior regions complete their orbits more rapidly than the exterior ones. At the nucleus, stars orbit at phenomenal speeds of approximately 225 kilometers per second, completing one full revolution in only a few million years. In the outer regions, the orbital velocities decrease, although not nearly as much as theory predicts, based solely on the visible matter. This fundamental discrepancy provides compelling additional evidence of the crucial presence of the dark matter halo, whose pervasive gravity significantly influences the motion of stars even at vast distances from the galactic center. The supermassive black hole at the very heart of Andromeda warrants special attention. With an estimated mass of approximately 100 million to 230 million solar masses, it significantly outclasses Sagittarius A star, the Milky Way's central black hole, which possesses only 4.3 million solar masses. This gravitational behemoth, though relatively inactive compared to the intensely active black holes in distant galactic nuclei, exerts a dominating gravitational influence over nearby stars. Detailed observations have revealed that some stars in the immediate vicinity of the black hole complete their orbits in less than 100 years, moving at incredible velocities that reach thousands of kilometers per second. Intriguingly, recent sophisticated studies suggest that Andromeda might harbor not just one, but two supermassive black holes in its nucleus. This highly unusual situation could be the direct result of a previous major galactic collision, where Andromeda successfully absorbed another significant galaxy, thereby inheriting its central black hole. If this compelling hypothesis is indeed correct, These two black holes will eventually merge, releasing gravitational waves of an extraordinary, cataclysmic intensity that could potentially be detected by specialized observatories even billions of light-years away. The dramatic history of Andromeda is permanently written in the delicate stellar streams that elegantly snake through its expansive halo. These fragile structures, composed of stars violently stripped from destroyed satellite galaxies, trace the violent history of galactic cannibalism. Andromeda has relentlessly devoured dozens of dwarf galaxies throughout its long existence, incorporating their stars and gas into its own burgeoning structure. One of these historic victims, nicknamed M32, still survives today as a compact satellite galaxy, but it has lost the majority of its original mass in repeated, brutal encounters with its massive gravitational master. Models strongly suggest that M32 was once a spiral galaxy of considerable size, but the powerful tidal forces of Andromeda have cruelly reduced it to a dense core encircled by a faint, wispy envelope of remaining stars. Looking toward the immediate future, in cosmic terms, Andromeda will continue to dominate our view of the night sky for millions of years. For observers on Earth, approximately 2 million years from now, Andromeda will appear noticeably larger in the sky, taking up more space. It will be in the subsequent billions of years that the true, magnificent spectacle will commence, transforming not only the sky, but potentially the very structure of the surrounding space near our solar system. With this deep understanding of the Andromeda Galaxy as our fundamental context, we are now fully prepared to immerse ourselves in the anatomical details of this galactic behemoth, exploring every facet of its impressive structure, from its brilliant core all the way out to the tenuous outer regions where the galaxy gradually fades into the intergalactic void. Part 2. Anatomy of a Giant. Andromeda in detail. To truly grasp the magnificent scale of the Andromeda Galaxy, we must dissect it layer by layer, revealing the deep secrets that reside within every region of this colossal cosmic structure. Imagine undertaking an impossible journey from the outermost fringes of Andromeda toward its incandescent core, traversing 110,000 light-years of galactic space. This voyage would reveal not only the physical anatomy of a cosmic giant, but also the epic story of billions of years of stellar evolution and dramatic history. Starting from the most distant borders of Andromeda, we encounter its highly extended galactic halo, a vast region that stretches far beyond the visible spiral disk. This halo, composed primarily of elusive dark matter mixed with sparsely scattered ancient stars, extends out to approximately 300,000 light-years from the galaxy's center. To put this into a powerful perspective, the halo of Andromeda is nearly as wide as 3 Milky Way galaxies, laid out side by side. In this extremely tenuous region, the stellar density is so incredibly low that you could travel thousands of light-years without encountering a single star. However, the halo is not entirely empty. Floating within this immense vastness, like remote islands in a cosmic ocean, we find Andromeda's remarkable globular clusters. These spherical objects contain anywhere from tens of thousands up to several million stars, tightly compacted into regions barely 100 light-years across. The 450 known globular clusters that currently orbit Andromeda are precious relics of the ancient past, having formed when the universe was only a few billion years old. Their stars, which are predominantly red and aged, glow with a dim but constant light, having long since exhausted the necessary fuel required to generate massive, hot blue stars. The brightest globular cluster in Andromeda, catalogued as G1 or Mayall 2, is an extraordinary object in its own right. With an approximate mass of 10 million solar masses, G1 is the most luminous known globular cluster in the entire local group. Situated about 130,000 light-years from Andromeda's center, this cluster contains several million stars, packed into a sphere of approximately 200 light-years in diameter. If our own solar system were located within G1, the night sky would present an utterly dazzling spectacle, with hundreds of stars shining with the intensity of Venus or greater, transforming the night into a perpetual, starry twilight. Moving inward, we cross into the majestic galactic disk of Andromeda. Here, the stellar density dramatically increases. The disk, with its characteristic flattened shape, extends approximately 110,000 light-years in radius from the galactic center, with a thickness that varies from only a few hundred light-years in the outer regions to approximately 3,000 light-years near the central bulge. This massive, disk-like structure is not merely a uniform distribution of stars, but a complex, dynamic ecosystem of gas, dust, magnetic fields, and multiple distinct generations of stars. Andromeda's disk is typically divided into several distinct components. The thin disk, where the majority of young stars and interstellar gas reside, has a thickness of approximately 1,000 light-years. Here we find massive blue stars that are barely a few million years old, as well as vast clouds of molecular hydrogen that glow faintly in radio wavelengths. The thick disk, an older and more vertically extended stellar population, reaches about 3,000 light-years in thickness and contains stars with typical ages ranging from 5 to 10 billion years. The spectacular spiral arms of Andromeda meander through the disk like luminous rivers in a dark sea. Unlike some spiral galaxies that exhibit brilliant and sharply defined arms, Andromeda's arms are more subtle, revealing themselves primarily in ultraviolet and infrared observations that detect hot young stars and dust clouds. Computer simulations suggest that these visible spiral arms are actually density waves, regions where galactic material is temporarily compressed, triggering spectacular bursts of star formation before the material continues its orbit around the galactic center. Star formation within Andromeda's disk follows fascinating patterns. H2 regions, which are clouds of ionized hydrogen surrounding massive newborn stars, dot the spiral arms like pearls on a magnificent necklace. The largest of these regions can span hundreds of light-years and contain sufficient mass to form tens of thousands of individual stars. Recent observations have identified more than 15,000 active star-forming regions within Andromeda, each one representing a stellar nursery where future generations of stars and planets are being born at this very moment. The interstellar gas within Andromeda's disk exhibits a complex chemical composition. Approximately 70% is hydrogen, 28% is helium, and the remaining 2% comprises the heavier elements, which astronomers collectively call metals, including carbon, oxygen, nitrogen, iron, and other elements forged in the cores of earlier stellar generations. This relatively high metallicity compared to the universe's earliest galaxies indicates that Andromeda has undergone multiple vigorous cycles of stellar formation, stellar death, and subsequent chemical enrichment throughout its more than 10 billion year history. Giant molecular clouds, the most massive structures in the interstellar medium, contain the majority of the dense gas within Andromeda's disk. These clouds, with masses ranging from thousands up to millions of solar masses, extend from tens to hundreds of light-years. Within them, extremely cold temperatures, barely 10 Kelvin above absolute zero, allow hydrogen molecules to form and persist. These frigid conditions are absolutely crucial for the gravitational collapse that eventually forms new stars. Penetrating deeper toward the center of Andromeda, the stellar density continues to increase exponentially. About 30,000 light-years from the nucleus, we enter what is termed the inner disk. where the average separation between stars shrinks to only a few light-years, compared to the approximately 4 light-years that separate our Sun from its closest stellar neighbor, Proxima Centauri. Here, close gravitational encounters between individual stars become notably more frequent on cosmological timescales, occasionally disrupting stellar orbits and perturbing potentially stable planetary systems. The central bulge of Andromeda dominates the inner regions of the galaxy. This spheroidal structure, extending approximately 10,000 light-years from the galactic center, contains an extraordinary concentration of very old stars. The bulge is estimated to harbor over 200 billion stars, meaning that approximately 20% of all of Andromeda's stars are compressed into less than 0.1% of its total volume. The stellar density in the central regions of the bulge reaches astonishing values, over 100 stars per cubic light-year, compared to a mere 0.004 stars per cubic light-year in the Sun's local neighborhood. If you could observe the night sky from a planet located within Andromeda's bulge, the spectacle would be awe-inspiring. Thousands of stars would shine with magnitudes comparable to those of the brightest planets seen from Earth. The sky would never truly be dark. Even during the night, the combined light from countless stars would provide sufficient illumination to easily read a book. The cumulative stellar radiation would significantly heat any exposed object, and the probability of a star passing close enough to gravitationally perturb planetary systems would be considerably higher than in the galaxy's outer reaches. The stars within the bulge are predominantly old, with typical ages ranging from 10 to 13 billion years, almost as ancient as the universe itself. Their chemical composition narrates the tale of Andromeda's earliest epochs. Many of these stars formed when the galaxy was still assembling from primordial gas clouds, at a time when the universe contained primarily hydrogen and helium, with only trace amounts of heavier elements. Successive generations of stars have gradually enriched the interstellar medium with heavier elements, but the oldest stars in the bulge preserve in their chemical makeup a precise record of the conditions that existed billions of years ago. Detailed spectroscopic studies have revealed that Andromeda's bulge is not a uniform stellar population, but contains multiple distinct components with varying formation histories. Some stars exhibit orbits that suggest they formed in situ during the gravitational collapse that initially gave rise to the bulge. Others display kinematic characteristics that indicate they were contributed by satellite galaxies that Andromeda ruthlessly devoured billions of years ago, their stars now dispersed and thoroughly mixed with the native population of the bulge. In the very heart of the bulge, less than 1,000 light-years from the absolute center of Andromeda, we approach one of the most extraordinary regions in the entire galaxy, the active galactic nucleus. Although Andromeda does not harbor an intensely energetic active nucleus like those observed in some distant quasars, its central region exhibits distinguishing characteristics. Here, the stellar density reaches its absolute maximum, exceeding 1,000 stars per cubic light-year in the closest vicinity to the central supermassive black hole. Andromeda's central black hole, with its immense mass of 100 million to 230 million suns, gravitationally dominates the nuclear region. Although it is invisible directly, its powerful presence is inferred from the extremely rapid orbits of nearby stars. Stars within 1 light-year of the black hole complete orbits in under a century, moving at incredible velocities that approach 1% of the speed of light. These dizzying speeds generate measurable relativistic effects. Time passes slightly slower for these stars compared to stars in more distant orbits, and the light they emit is redshifted due to the intense gravitational fields. The immediate region surrounding the central black hole presents a hostile environment for any form of life. High-energy radiation originating from matter that occasionally spirals into the black hole. though far less intense than in violently active galactic nuclei, is still sufficient to sterilize any planet within several light-years. Close gravitational interactions between stars are frequent in this densely packed region, making it highly improbable that stable planetary systems could survive for prolonged periods. Intriguingly, recent observations suggest an unusual structure in Andromeda's nucleus. Instead of a simple stellar core centered on the black hole, there appears to be a double structure, featuring two distinct concentrations of stellar light, separated by approximately 5 light-years. One possible interpretation is that we are observing the result of a past galactic collision, where Andromeda absorbed another significant galaxy. The two cores might represent the surviving remnants of the centers of both galaxies, still in the slow process of fully merging. Alternatively, the double structure could be an effect produced by a disk of stars orbiting the central black hole, viewed from a particular favorable angle. The hypothesis of two black holes at Andromeda's center, though not yet definitively confirmed, carries fascinating implications. If correct, these two gravitational monsters will eventually orbit closer and closer to each other, losing orbital energy through the vigorous emission of gravitational waves. In their final death spirals, they would complete thousands of turns per second before finally merging into a single, even more massive black hole, releasing during the process an amount of energy in the form of gravitational waves equivalent to the conversion of several solar masses into pure energy. This cataclysmic event, when it occurs in the far future, will be one of the most energetic occurrences in Andromeda's long history. Surrounding the galactic nucleus and extending out to a few thousand light-years, we find stellar populations with peculiar characteristics. Some regions exhibit clear evidence of relatively recent episodes of star formation, containing stars merely a few 100 million years old, quite young compared to the overall age of the bulge. This discovery initially surprised astronomers, as the central regions of massive galaxies are generally considered dead in terms of star formation, having consumed or expelled most of their gas billions of years ago. The most likely explanation for this recent star formation in Andromeda's core involves the slow accumulation of gas transported from the galaxy's outer regions. Gravitational perturbations, possibly caused by interactions with satellite galaxies or by the weak bar structure that some studies suggest exists in Andromeda, can efficiently channel gas toward the galactic center. Once there, the gas is compressed by the intense gravity, eventually reaching sufficient densities to collapse and form new stars. Scattered throughout Andromeda's bulge and disk, we find the ubiquitous remnants of dead stars, white dwarfs, dense cores the size of Earth but with masses comparable to the Sun, represent the corpses of low and medium-mass stars that have exhausted their nuclear fuel. Andromeda is estimated to contain several hundreds of billions of white dwarfs, many of them quietly cooling into darkness, invisible even to the most powerful telescopes. Some of these white dwarfs participate in binary systems, where they slowly accumulate material from a companion star, a process that occasionally culminates in thermonuclear explosions known as Type 1a supernovae. Neutron stars, even more extreme objects with solar masses compressed into spheres barely 20 kilometers in diameter, also populate Andromeda in significant quantities. These objects, the remnants of massive stars that exploded as supernovae, possess magnetic fields billions of times more intense than Earth's and spin at breakneck speeds, some completing hundreds of rotations per second. Pulsars, which are neutron stars that emit beams of radiation from their magnetic poles, sweep across space like cosmic lighthouses. To date, several pulsars have been detected within Andromeda, though the distance of 2.5 million light-years makes their observation extremely challenging. Stellar mass black holes, with masses typically between 5 and 50 times that of the Sun, represent the final destination of the most massive stars. These objects, completely invisible except for their gravitational effects on surrounding matter, likely exist in quantities of tens to hundreds of millions within Andromeda. The majority remain solitary, silently wandering the galaxy, but some participate in binary systems, where their intense gravity rips material from a companion star, producing brilliant X-ray emissions as the infalling material heats up to millions of degrees before finally disappearing beyond the event horizon. The total mass of Andromeda, considering all these components, remains one of the most vigorously debated parameters in modern galactic astronomy. Estimates vary considerably depending on the methodology used. Techniques based on the kinematics of stars and globular clusters suggest a total mass of approximately 1.5 trillion solar masses. However, when the highly extended dark matter halo is included, which may stretch up to 500,000 light-years or more from the galactic center, some estimates elevate the total mass to 2 trillion solar masses, or even higher. This intrinsic uncertainty in mass has significant consequences for predicting the future encounter between Andromeda and the Milky Way. A more massive Andromeda would exert a stronger gravitational pull, accelerating the collision process and altering the precise details of how the two galaxies will interact. Increasingly precise measurements of the velocities of objects in Andromeda's outer regions are helping to refine these critical estimations, but determining the exact mass of such a vast object distributed over such an enormous volume remains one of the most difficult observational challenges in astronomy. With this detailed comprehension of Andromeda's anatomy, from its tenuous outer halo to its dense central nucleus, from its spiral arms populated by young stars to its bulge of ancient stars, we are fully prepared to explore the defining event that will shape the future of both galaxies, the inevitable collision that will forever transform the local group. The distribution of matter within Andromeda reveals fundamental patterns that tell the story of its evolution over billions of years. The metallicity gradient, the variation in the abundance of heavy elements from the center toward the outer regions, shows a pattern typical of massive spiral galaxies. Highest metallicity at the center, gradually decreasing toward the periphery. This pattern reflects the fact that the galaxy's core has experienced more generations of star formation, producing and dispersing more heavy elements forged in the cores of massive stars that eventually exploded as supernovae. However, this gradient is not perfectly smooth. Detailed observations have revealed irregularities that suggest complex episodes of mixing and enrichment. Some regions in the outer disk show surprisingly high metallicities, possibly the result of gas flows transported from the inner regions by galactic winds or by the disk's differential rotation. Other regions exhibit unexpectedly low metallicities, perhaps recently accrued pristine gas from the intergalactic medium, or the remnants of metal-poor satellite galaxies that were absorbed by Andromeda. Andromeda's magnetic field, although extremely weak, plays crucial roles in galactic physics. With intensities of just a few microgauss, the galactic magnetic field influences the movement of ionized gas and confines high-energy cosmic rays. Radio observations have revealed that it generally follows the spiral arms, with complexities in the inner regions where turbulence distorts its configuration. Interstellar dust, although constituting only about 1% of the interstellar medium's mass, absorbs ultraviolet and optical light, re-emitting it in the infrared. Infrared observations successfully penetrate this veil, revealing hidden stellar populations. The Spitzer telescope captured concentric rings of star formation 10,000 and 30,000 light-years from the center, possibly the result of orbital resonances. Andromeda's current star formation rate, approximately 1 solar mass per year, represents a relatively quiescent state. However, throughout its history, it has experienced much more intense periods, particularly during collisions with satellite galaxies. Evidence of these episodes remains in groups of stars with similar ages that betray synchronized star formation thousands of millions of years ago. Andromeda's satellite galaxies form an integral part of its gravitational ecosystem. M32, the compact elliptical satellite galaxy previously mentioned, is one of the most intriguing examples. With a mass of approximately 3 billion solar masses compressed into a radius of barely 1,500 light-years, M32 is extraordinarily dense. Its origin remains enigmatic. Is it the surviving nucleus of a much larger spiral galaxy that was stripped of its outer regions by repeated encounters with Andromeda? Or did it form as a compact elliptical galaxy from the outset? Computer simulations and increasingly detailed observations are beginning to favor the former hypothesis. M110, another prominent satellite galaxy of Andromeda, presents contrasting characteristics. This dwarf elliptical galaxy, with approximately 10 billion solar masses, shows evidence of relatively recent star formation, which is unusual for elliptical galaxies that typically contain only old stars. The cause of this recent star formation is likely related to powerful tidal interactions with Andromeda, where gravitational forces compress the gas within M110, triggering episodes of stellar birth. Numerous additional spheroidal dwarf galaxies orbit Andromeda at distances varying from tens of thousands up to several 100,000 light-years. These diminutive galaxies, with typical masses of only a few million to tens of millions of solar masses, are extremely faint, detectable only with sensitive telescopes. Their importance transcends their modest appearance. Theories of structure formation in a dark matter-dominated universe predict that massive galaxies like Andromeda should be surrounded by hundreds or even thousands of small satellite galaxies. However, only a few dozen have been detected so far. This discrepancy, known as the missing satellite problem, represents one of the unresolved challenges in modern cosmology. The spectacular stellar streams enveloping Andromeda provide dramatic evidence of its history of galactic cannibalism. These long, extended, and tenuous structures, composed of stars violently ripped from satellite galaxies by tidal forces, snake through Andromeda's halo like gravitational scars. The most prominent stellar stream, called the Giant Southern Stream, extends over 100,000 light-years and contains stars that were likely once part of a satellite galaxy that Andromeda destroyed approximately 1 billion years ago. The study of these stellar streams is not merely galactic archaeology. The properties of the streams, including their orbits and velocity dispersion, provide crucial information about the distribution of dark matter within Andromeda's halo. The dark matter, although invisible, exerts gravitational forces that affect the movement of the stars in the streams. By comparing the observed orbits with theoretical model predictions, astronomers can infer properties of the dark matter halo, including its total mass and its density profile. Andromeda's future evolution, even without the collision with the Milky Way, would follow a fascinating path. Its star formation will diminish as gas is gradually depleted. Its satellite galaxies will be slowly absorbed. In tens of billions of years, it would evolve into a dead elliptical galaxy containing only old red stars. However, Andromeda will not exist in isolation. Its destiny is inextricably intertwined with that of the Milky Way. The gravitational dance has already begun, and its climax will transform both galaxies beyond recognition. To truly understand this shared fate, we must now turn our attention to the event that will define the next billions of years of the local group's history: the inevitable collision between Andromeda and the Milky Way. Part 3. The inevitable collision: simulations and chronology. The discovery that the Andromeda galaxy is inexorably approaching the Milky Way represents one of the most dramatic findings in the history of modern astronomy. For many decades, astronomers observed distant galaxies receding from us, their light spectroscopically shifted toward the red end of the spectrum by the relentless expansion of the universe. Andromeda, however, defiantly challenges this universal pattern. Its light exhibits a compelling blue shift, an unmistakable spectroscopic signature that this giant galaxy is hurtling toward us at a velocity that vastly exceeds any ordinary orbital movement within the local group. The initial measurements of Andromeda's radial velocity, conducted in the 19-teens by Vesto Slipher using pioneering spectroscopy, revealed this approaching motion. However, knowing that Andromeda is approaching is only half of the equation. The truly crucial question remained: would Andromeda merely pass by the Milky Way in a perturbing but non-catastrophic gravitational encounter, or would these two galactic titans collide head-on? For nearly a century, this question lacked a definitive answer. The reason is technical but fundamental. Measuring the speed at which an object approaches or recedes is relatively straightforward through spectroscopy, but determining its transverse motion across the sky, its sideways movement, requires extraordinarily precise position measurements sustained over decades. In 2012, a dedicated team of astronomers utilizing the Hubble Space Telescope finally resolved this long-standing question. By carefully observing the positions of individual stars in Andromeda over several years, they measured a minuscule yet measurable transverse motion. The subsequent calculations were absolutely unequivocal. Andromeda will not graze past the Milky Way. It is headed directly toward us on a frontal collision trajectory. The probability that the two galaxies will eventually merge is virtually 100%. It is not a question of if it will occur, but of when and how this cosmic cataclysm will unfold. Sophisticated computer simulations, fed with the precise masses, velocities, and trajectories of both galaxies, have allowed astronomers to predict the course of this galactic collision with remarkable detail over the next billions of years. These elaborate models, executed on powerful supercomputers that meticulously track the gravitational movement of millions of particles representing stars, gas, and dark matter, reveal a cosmic ballet of astonishing complexity that will develop in slow motion over a significant fraction of the universe's current age. The predicted chronology commences in the present. Today, December 13, 2025, Andromeda is located 2.537 million light-years away, approaching us at a velocity of approximately 110 kilometers per second. This speed may seem dizzying, and it is on human scales, but in cosmic terms it is nearly glacial. At this rate, Andromeda reduces the distance separating us by approximately 3.5 billion kilometers per year, a figure that sounds impressive until we consider that the total distance yet to be covered is approximately 24 quintillion kilometers. The time it will take to cover this vast distance is, therefore, about 4 billion years. However, the speed of approach will not remain constant. As the two galaxies draw nearer, the mutual gravitational attraction intensifies dramatically, accelerating the entire process. Within approximately 2 billion years, hypothetical observers on Earth would begin to notice visible changes in the night sky. Andromeda, which currently appears as a diffuse smudge barely visible to the naked eye, will start to noticeably expand in the firmament. Its disk, previously so faint that only the bright nucleus was clearly visible, will begin to reveal its structure. The magnificent spiral arms populated by young blue stars will become apparent even without the aid of telescopes. Within 2.5 billion years, Andromeda will spectacularly dominate the night sky. It will occupy an area several times larger than the full moon, stretching across tens of degrees of the celestial arc. Its concentrated nucleus will shine with the combined intensity of hundreds of individual stars. For the inhabitants of Earth at that epoch, should humanity or its descendants still exist, the night sky will be fundamentally and irrevocably different from the one we know today. Two galactic disks, that of the Milky Way viewed from within and that of Andromeda approaching from without, will majestically divide the celestial vault between them. Within 3 billion years, the powerful gravitational effects of the approach will begin to manifest in subtle yet measurable ways. The outermost regions of both galaxies, where gravity is weakest and the stars are more dispersed, will begin to be dramatically distorted by strong tidal forces. Streams of stars will be violently ripped from the edges of both galactic disks, creating immense tidal bridges and tails that will extend hundreds of thousands of light-years into intergalactic space. These enormous structures, visible in simulations of galactic collisions observed in distant galaxies, will bear witness to the beginning of the final gravitational embrace. Approximately 3.75 billion years from now marks a crucial moment, the first pericenter, the point of closest approach in the initial encounter. At this critical time, the outer regions of both galaxies will interpenetrate. However, it is essential to understand that galactic collision is a term that can be misleading. Galaxies do not collide like solid, rigid objects. The space between the stars is so vast that the probability of any two individual stars physically colliding during the encounter is astronomically small, almost negligible. A useful analogy: if we represent each star as a single grain of sand, the average distance between grains of sand in a galaxy would be several kilometers. Galaxies are, for the most part, entirely empty space. Nonetheless, although the stars themselves do not physically collide, their powerful gravitational fields interact intensely. Every star in Andromeda exerts a minuscule gravitational force on every star in the Milky Way, and vice versa. The summation of these infinitesimal interactions produces dramatic, large-scale effects. During the first pericenter, the relative velocity of the two galaxies will be extremely high, possibly exceeding 200 kilometers per second. They will not have sufficient time to fully merge in this first encounter. Instead, they will pass through each other, violently distorting themselves in the process. The detailed simulations show that after this initial close encounter, the two galaxies will continue to separate, albeit much more slowly than they approached. Mutual gravity has effectively stolen angular momentum and kinetic energy from the system. Like two cosmic dancers connected by invisible gravitational strings, Andromeda and the Milky Way cannot fully separate. Within approximately 5 billion years from now, the galaxies will reach their maximum separation following the first encounter, approximately 500,000 light-years, before gravity relentlessly drags them back together for a second, even more intimate encounter. This second pericenter, predicted for approximately 5.5 billion years from the present, will be even more chaotic than the first. The structures of both galaxies, already distorted by the initial encounter, will be further dramatically deformed. The magnificent spiral arms, so carefully organized into coherent structures for billions of years, will dissolve into chaotic, disorganized stellar streams. The interstellar gas, which in normal galaxies flows smoothly in organized orbits, will undergo massive, violent collisions. Unlike the stars, the gas can and will physically collide, and these collisions will be spectacular events. When monumental clouds of gas from both galaxies collide at speeds of hundreds of kilometers per second, they will be violently compressed and heated. This extreme compression process will trigger star formation on an unprecedented scale. Entire regions of space, containing masses equivalent to billions of suns in gas, will collapse simultaneously, producing what astronomers term a massive stellar explosion, or starburst. During this frenetic period, the rate of star formation in the combined Andromeda-Milky Way system could increase 100-fold or more above the current rate, creating hundreds of solar masses in new stars every single year. These newly formed stars will not be ordinary. Many will be extremely massive, tens or even hundreds of times more massive than the Sun. These giant stars will blaze with intensities that exceed the solar luminosity by millions of times, bathing the merging galaxies in an intense, brilliant blue-white light. However, their glory will be fleeting. The most massive stars consume their nuclear fuel with prodigious speed, burning out in only a few million years before dramatically exploding as supernovae. The supernova rate during the peak of the starburst could reach several per year, compared to approximately one every 50 years in the current Milky Way. Each supernova will release as much energy in a few months as the Sun will emit during its entire 10 billion-year lifespan. The intense radiation and shock waves from these explosions will sterilize vast regions of space, but they will also seed the interstellar medium with heavy elements forged in the cores of the dying stars, enriching the material from which future generations of stars and planets will eventually form. After the second paracenter, the two galaxies will again separate, but this time the separation will be smaller and slower. Orbital energy has been significantly dissipated. A third, even more intimate encounter will follow. With each pass, the orbits of the stars become more randomized, the orderly galactic disks gradually transforming into chaotic spheroidal distributions. Models predict that after approximately 7 billion years from the present, the multiple passes will have so completely mingled the two galaxies that they will no longer be distinguishable as separate entities. The final product of this cataclysmic merger will be a single, gigantic elliptical galaxy. Unlike spiral galaxies with their thin disks and elegant arms, elliptical galaxies are spheroidal or ovoid structures, lacking distinctive organized features. Stars in elliptical galaxies orbit the center on random, chaotic trajectories in all directions, without the organized, circular motion characteristic of spiral disks. This newly formed galaxy, informally dubbed Milkomeda or Lactomeda by astronomers, will contain all the stars from both progenitor galaxies, approximately 1.4 trillion suns. Lactomeda will be one of the most massive objects in the resulting local group, gravitationally dominating its cosmic neighborhood. Its size will be considerable, with an effective radius of perhaps 100,000 light-years, although individual stars and stellar streams could extend much further. The precise final shape of the resulting galaxy will depend on specific details of the encounter, particularly the relative orientations of the galactic disks during the closest passes and the precise distribution of dark matter in the halos of both galaxies. At the very heart of Lactomeda will reside a single supermassive black hole, the product of the merger between the central black holes of Andromeda and the Milky Way. This combined black hole will have a mass of approximately 110 million to 240 million solar masses, the sum of its progenitors. The merging process of two supermassive black holes is one of the most energetic events conceivable in astrophysics. In the final stages, when the two black holes orbit merely a few Schwarzschild radii apart, they will complete orbits thousands of times per second, emitting gravitational waves of extraordinary intensity. These gravitational waves, which are ripples in the very fabric of space-time predicted by Einstein's theory of general relativity, will carry away energy equivalent to several % of the total mass of the black holes. To put this into perspective, if the two black holes have a combined mass of 200 million solar masses, and 3% of this mass is converted into gravitational wave energy, the energy released will be equivalent to 6 million solar masses being completely converted into pure energy, according to the famous equation E equals mc squared. This stupendous amount of energy, liberated in a matter of mere minutes during the final fusion, will briefly exceed the combined luminosity of all the stars in the observable universe. However, unlike light, which can be blocked by intervening matter, gravitational waves propagate through space virtually unimpeded. Gravitational wave observatories in distant galaxies, should technological civilizations be operating them billions of years in the future, would easily detect this event from billions of light-years away. It would be one of the most luminous gravitational wave events in the history of the local universe. The galactic merger will also have profound effects on the smaller satellite galaxies of the local group. The Triangulum galaxy, M33, currently orbiting Andromeda, will be inevitably drawn into the conflagration. Depending on the specifics of its orbit and the precise timing of the Andromeda-Milky Way merger, M33 could merge with the system before, during, or after the main encounter. Its relatively small mass, approximately 10% of the Milky Way's, means its contribution to the final product will be minor, but its stars will add to the growing swarm that eventually forms Andromeda. The remaining dwarf galaxies of the local group will experience varied destinies. Some, particularly those on distant orbits, might survive as satellites of Andromeda. Others will be violently torn apart by tidal forces during the chaotic encounters, their stars dispersed into streams that eventually incorporate into the halo of the resulting galaxy. A few might even be ejected completely from the system by violent gravitational slingshot encounters, becoming rogue galaxies in intergalactic space, condemned to wander eternally far from any galactic group. Throughout this entire process, which will span billions of years, it is crucial to appreciate the immense timescales involved. From the human perspective, even 1,000 years is an eternity that exceeds all of recorded civilization's history. 1,000,000 years is almost incomprehensible, surpassing the entire existence of Homo sapiens as a species by a factor of 5. 1,000,000,000 years is a temporal scale over which entire planets are born and die, over which biological evolution radically transforms life, over which stars complete entire cycles of existence. The events we have described will unfold slowly, imperceptibly on human timescales. If you could observe the sky every single night for a complete human lifetime at any point during the merger, you would see essentially nothing change. The stars would remain in the same relative positions. Andromeda would expand in the sky, but so gradually that only precise measurements could detect the change from year to year. It would be like trying to watch the movement of a clock's hour hand, but slowed down by millions of times. However, on timescales of millions of years, the changes would be dramatic and obvious. The night sky would be utterly transformed. The constellations, those familiar figures that humans have observed for tens of thousands of years, would dissolve as the stars dispersed into new configurations. New, brilliant stars would appear as star formation accelerates. The combined glow from billions of stars in the central regions of the merging galaxies could illuminate the night sky to the point that true darkness would be unknown during the peak of the starburst. To fully comprehend the implications of this galactic merger, we must now turn our attention to a question that undoubtedly concerns anyone who contemplates these cosmic events. What will happen to the Earth and the solar system during this grand transformation of the local group? Will we survive the monumental encounter? And if so, under what conditions will we find ourselves? Computer simulations have achieved an extraordinary level of sophistication in recent decades. Modern models can track the movement of billions of particles, each representing a portion of galactic mass, as they evolve under the influence of gravity over cosmological timescales. These models incorporate not only the stars, but also the interstellar gas, the dark matter, and even complex physical processes such as star formation, supernova explosions, and the energetic feedback from active black holes. The results of these simulations are visually spectacular and scientifically revealing. When visualized as animations that compress billions of years into mere minutes of video, they unveil a gravitational choreography of hypnotic beauty. The two spiral galaxies slowly approach, initially maintaining their majestic structures. As they draw near the first paracenter, the disks begin to dramatically distort, developing exaggerated spiral arms that reach out toward the neighboring galaxy like gravitational tentacles. During the closest pass, luminous bridges of stars and gas form between the galaxies, shining channels that transport material from one system to the other. Simultaneously, massive tidal tails, composed of stars violently ripped from the outer regions of both galaxies, project in opposite directions, extending hundreds of thousands of light-years into intergalactic space. These tails will eventually curve back due to gravity, some of their components falling back into the merging galaxies, others becoming permanently dispersed. The precision of these simulations has improved dramatically over time. Early simulations, executed in the 1970s and 1980s, could track only thousands or tens of thousands of particles. Modern models, executed on supercomputers performing quadrillions of operations per second, routinely track billions of particles, allowing for resolutions that capture details down to individual light-year scales. This vast improvement has enabled increasingly reliable predictions, not only of the global evolution of the merging galaxies, but also of the fates of specific structures within them. One particularly fascinating feature revealed by modern simulations is the behavior of the gas during the collision. Unlike the stars, which pass by one another like bees in interpenetrating swarms, the gas can and does collide. When clouds of molecular gas from both galaxies crash into each other at speeds of hundreds of kilometers per second, the resulting shock waves compress the gas to extreme densities. This compression can be so intense that it overcomes the forces that normally stabilize the clouds against gravitational collapse. The outcome is massive, synchronized star formation on a galactic scale. Entire regions of space, spanning tens of thousands of light-years, can ignite almost simultaneously with the brilliant light of millions of newborn stars. The most massive of these stars, with masses 50, 100, or even 200 times that of the Sun, will shine with intensities that rival entire small galaxies. These ultramassive stars are extremely rare in normal galaxies like the current Milky Way, but they could become relatively common during the peak starbursts induced by mergers. However, the glory of these giant stars is ephemeral. The most massive stars exhaust their nuclear fuel in only a few million years, a mere blink on cosmic timescales. When they finally collapse, they do so spectacularly, exploding as supernovae that release as much energy in weeks as the Sun will emit in its entire billion-year lifespan. Some might even produce gamma-ray bursts, the most luminous electromagnetic events known in the universe, capable of emitting more energy in seconds than the Sun does over its complete life. The energy liberated by these supernovae does not simply vanish. The shock waves sweep through the interstellar medium, heating it to millions of degrees. This process, called supernova feedback, can eject gas from the galaxy if enough supernovae explode in a concentrated region. This process of gas expulsion has crucial implications for the future of star formation in Andromeda. Gas is the essential fuel for the formation of new stars. If large quantities are expelled during the starburst phase of the merger, the subsequent rate of star formation will dramatically decline. Indeed, many massive elliptical galaxies observed in the current universe have very low, almost non-existent star formation rates, presumably because they consumed or expelled the majority of their gas during violent events in their past, very likely galactic mergers. Andromeda will likely follow this pattern. During the peak of the merger, approximately 5 to 6 billion years from now, star formation will be frenetic. But within 7 to 8 billion years, once the merger is complete, star formation will almost entirely cease. Andromeda will become a red and dead galaxy, populated by old stars with no active star-forming regions. The central black holes of both galaxies will also play important roles during the merger. As the two galaxies merge, their central black holes will sink toward the center of the resulting galaxy, a process called dynamical friction decay. Initially, the black holes will be separated by tens of thousands of light years, but gravitational friction with surrounding stars will gradually steal their orbital energy, causing their orbits to decay. Once the black holes approach within a few light years of separation, they begin to form a bound binary system. At this point, the emission of gravitational waves becomes the dominant mechanism for energy loss. The orbits contract faster and faster, and the orbital frequency increases. In the final climactic stages, mere seconds before the fusion, the black holes will orbit thousands of times per second, emitting gravitational waves so intense that they will literally distort space-time in their immediate vicinity. The final merger will be extremely violent. The two event horizons will combine, forming a single distorted event horizon that rapidly relaxes to a spherical shape, ringing like a struck bell. These oscillations, called quasi-normal modes, will emit the final intense gravitational waves before the system stabilizes as a single, rotating, supermassive black hole. The resulting black hole might receive what is called a gravitational kick. Due to the asymmetric emission of gravitational waves during the merger, the black hole can acquire a recoil velocity, potentially hundreds of kilometers per second. In extreme cases, this velocity could be sufficient to eject the black hole entirely from the galaxy's core. However, for the Andromeda-Milky Way merger, the parameters of the black holes suggest that any kick will be modest, insufficient for expulsion, although it could displace the black hole several hundred light-years from Andromeda's geometric center. While all this unfolds on galactic scales, what will observers on individual planets experience? For the vast majority of the merger, surprisingly little in terms of direct physical effects. The distances between stars are so enormous that the local space around any individual star remains relatively undisturbed. However, the heavens would change dramatically. During the early phases of approach, observers on Earth would see Andromeda slowly expand night after night, year after year, century after century. Its angular size would increase from the current 3 degrees to 10 degrees, then to 30 degrees, eventually spanning a quarter of the visible sky. Its internal structure would become apparent: spiral arms, star-forming regions, dark dust clouds, all visible to the naked eye. During the first pericenter, the sky would be dominated by the two galaxies. From Earth, we would see the Milky Way disk stretching across the sky as always, but now sharing the firmament with the massive disk of Andromeda. Depending on the exact orientation during the encounter, the two disks might appear nearly perpendicular to each other, creating a cosmic cross of starlight that divides the sky into quadrants. The starbursts induced by the collision would add fireworks to the spectacle. Entire regions of the sky would light up with the intense blue-white glow of millions of massive young stars. Supernovae, occurring perhaps several times per year during the peak of activity, would appear as bright new stars that suddenly surge, reaching luminosities that would rival Venus or even the Moon, and then fade over weeks or months. In the final stages of the merger, when the disk structures have completely dissolved into a spheroidal distribution, the sky would present an entirely different appearance. Instead of the familiar band of the Milky Way, there would be a more or less uniform distribution of stars in all directions, denser toward the center of Andromeda, fainter toward the outer regions. The familiar constellations would have vanished long ago, replaced by entirely new, transient patterns formed by randomly dispersed stars. For hypothetical civilizations that survive, the event would offer unprecedented scientific opportunities. The physics of star formation under extreme conditions, the dynamics of black hole mergers, stellar evolution in chaotic environments, all could be studied in detail, impossible to achieve otherwise. However, the gravitational perturbations during the merger could affect the stability of planetary systems. Close encounters with other stars could perturb the orbits of planets, especially outer ones, or launch comets toward the inner regions, causing catastrophic bombardments. The exact probability of such events for the solar system specifically will be the subject of our next exploration. But before we turn our attention to our own destiny, it is worthwhile to contemplate the temporal and spatial scale of the events we have described. The Andromeda-Milky Way merger is an event of truly cosmic significance, one that will completely transform the structure of the local group over billions of years. It serves as a profound reminder that even the seemingly permanent structures of the cosmos, the galaxies themselves, are not eternal and immutable, but dynamic entities that evolve, interact, and transform on the vast timescales of cosmic history. Part 4. The Fate of Earth and the Solar System. The question that inevitably arises when contemplating the collision between Andromeda and the Milky Way is deeply personal. What exactly will happen to Earth? Will our planet, will our solar system, survive this grand galactic cataclysm? To answer these fundamental questions, we must meticulously examine the probabilities, the possible trajectories, and, perhaps most importantly, acknowledge a sobering truth that is often overlooked in discussions about the galactic collision. Let us begin with the seemingly good news, or at least the news that appears comforting at first glance. As we have established, the probability that the Sun will directly collide with another star during the galactic merger is extraordinarily small. Calculations consistently suggest a probability of less than 0.01%, which is essentially zero in practical terms. This is entirely due to the immense distances between stars. Even during the chaos of a galactic collision, when billions of stars interpenetrate, the space between them remains so vast that direct encounters are statistically improbable. However, this does not signify that the solar system will remain completely unaltered. During the merger, the Sun's orbit around the galactic center will be dramatically perturbed. Currently, the Sun orbits the Milky Way's center at a distance of approximately 26,000 light-years, completing one revolution every 225 million years in a relatively circular and orderly orbit. During the merger, this ordered orbit will descend into chaos. Computer simulations that track the trajectories of individual stars during galactic mergers reveal a variety of possible fates. Approximately 12% of the stars in both galaxies will be ejected completely from the merged system, flung into intergalactic space at velocities that exceed the escape velocity. These rogue stars will travel eternally through the vacuum between galaxies, forever receding from Andromeda. If the Sun were one of these ejected stars, the Earth and the other planets would presumably accompany it, as the forces ejecting the star are gravitational and act upon the entire system equally. For a planet orbiting an ejected star, the consequences would be profound, but perhaps not immediately catastrophic. The night sky would change dramatically. Instead of being surrounded by the lights of billions of stars in our galaxy, observers would witness an almost completely black firmament, punctuated only by a few scattered stars, other exiles traveling in similar directions. Far in the distance, Andromeda would appear as a slowly shrinking luminous smudge as we sped away. Neighboring galaxies in the local group, if they still existed as separate entities, would be barely visible as faint patches. Approximately 3% of the stars will experience the opposite fate. They will be hurled inward toward the central regions of Andromeda, sinking toward the dense galactic core. For these stars, the environment would become increasingly crowded. The probability of close encounters with other stars would significantly increase. Although a direct collision would still be unlikely, encounters close enough to perturb planetary orbits would become more common. Outer planets could be violently stripped from their systems, while inner planets might see their orbits altered in ways that would render them uninhabitable. For the majority of stars, approximately 85%, the destiny will be less dramatic, but still significant. They will remain bound to Andromeda, but in orbits vastly different from those they held in their original galaxies. Some will move in highly elliptical paths that will periodically carry them close to the galactic center and then back out to the outer regions. Others will settle into the spheroidal halo of Andromeda, orbiting in random directions without the characteristic ordered movement of galactic disks. What will be the specific fate of the Sun? Given our current position in the Milky Way, roughly 2/3 of the way from the center to the edge, in a relatively circular orbit, models suggest that the most likely outcome is that we will remain bound to Andromeda, albeit in a significantly altered orbit. The probability of expulsion exists, but it is less than the average due to our moderate distance from the galactic center. Stars in the outermost regions of both galaxies have a higher chance of being ejected, while those in the center have a higher chance of remaining deeply trapped in the gravitational well of the merged galaxy. However, there is a crucial, overarching factor that must be emphasized, a detail that completely transforms our understanding of Earth's destiny during the galactic collision. This detail has nothing whatsoever to do with the gravitational perturbations of other stars or our potential expulsion from the galaxy. It has everything to do with the Sun itself. The Sun is not eternal. It is a G-type main-sequence star that currently has an age of approximately 4.6 billion years. Stars like the Sun have finite lifespans, determined by the amount of hydrogen in their cores that can be fused into helium. When that critical fuel is exhausted, the Sun will undergo dramatic, predictable changes. Stellar evolution models predict with considerable confidence what will happen to the Sun in the future. Within approximately 1 billion years, the Sun's luminosity will have increased by about 10% above its current value. This increase may sound modest, but it will have profound consequences for Earth. The global temperature will gradually rise. The oceans will begin to evaporate more quickly. Water vapor in the atmosphere, a potent greenhouse gas, will amplify the warming. This positive feedback process will accelerate the heating until, eventually, the oceans completely evaporate. Earth will turn into a desiccated, sterile desert world, similar to present-day Venus. Within approximately 3.5 billion years, long before the galactic collision reaches its climax, Earth will be almost certainly uninhabitable for any form of complex life. The surface will be far too hot, the atmosphere too dense with water vapor, and the solar radiation too intense. Any life that persists will do so in extremely specialized niches, perhaps deep underground, where temperatures remain tolerable. Within approximately 5 billion years, almost exactly when predictions place the second pericenter of the Andromeda-Milky Way collision, the Sun will completely exhaust the core hydrogen fuel. At that point, it will begin fusing hydrogen in a shell around the inert helium core. This transition will cause the Sun to expand dramatically, turning into what astronomers call a red giant. During this phase, the Sun will swell to an enormous size. Its radius will increase from the current approximately 696,000 kilometers to perhaps 150 million kilometers or more, roughly the current distance from the Earth to the Sun. The outer, hugely expanded and tenuous layers of the Sun could potentially extend beyond Earth's orbit. If this occurs, the Earth will be literally engulfed by the Sun's outer atmosphere. Even if Earth manages to avoid being completely swallowed, which is uncertain and depends on details such as how much mass the Sun will lose during its expansion, the consequences will be catastrophic. The temperature at Earth's orbit will soar to thousands of degrees. Any remaining atmosphere Earth possesses will be stripped away. The surface will melt, turning into a global ocean of molten rock. All volatile components, water, carbon, nitrogen, will evaporate and be swept away by the intense stellar winds of the red giant. Within approximately 7 billion years, when the galactic merger is finally completing and Andromeda is emerging as a unified elliptical galaxy, the Sun will have passed through the red giant phase and will have become a white dwarf, a dense, hot core roughly the size of Earth, but with a mass comparable to the Sun's. Earth, if it still exists as a distinguishable physical body, will be a dead, sterile, airless world, possibly molten on its surface, orbiting the dying embers of our Sun. This is the sobering truth, often omitted in popular discussions of the Andromeda-Milky Way collision. Humanity will not be here to witness it. Or, more precisely, unless humanity or its descendants have developed technologies enabling migration to other star systems, life on Earth as we know it will have ceased long before the galactic collision reaches its most dramatic stages. The cosmic spectacle we have described in detail, the interpenetrating galaxies, the starburst explosions, the merging of supermassive black holes, all of this will occur, but Earth will be a dead world when it happens. The fate of the solar system during the galactic collision, whether it will be ejected or remain bound to Andromeda, is largely academic compared to the much more immediate and unavoidable destiny we face, the natural evolution of our own Sun. Nevertheless, let us briefly contemplate a counterfactual scenario. Suppose that, somehow, Earth could be kept habitable during the galactic collision, perhaps through massive technological interventions to counteract the rising solar luminosity. Or, let us assume that humanity has successfully migrated to other planets orbiting longer-lived stars. What would observers experience during the merger? The night sky would be the most obvious and dramatic change. For billions of years, humanity has observed essentially the same sky. Constellations change slowly due to the proper motion of stars, but on timescales of thousands or even tens of thousands of years, they remain recognizable. During the galactic merger, this would radically change. Within 2 billion years, Andromeda would be visible as a massive structure in the sky, occupying an area several times larger than the full moon. Its disk would be clearly visible, with discernible spiral arms to the naked eye. Star-forming regions would glow with a bluish tint. Dark dust clouds would trace complex patterns across the disk. For observers, it would be like having 2 Milky Ways in the sky simultaneously. During the first pericenter, approximately 3.75 billion years from now, the sky would be completely dominated by galactic structures. The 2 disks, the Milky Ways viewed from within and Andromeda's viewed from without, would partially overlap. Depending on the exact orientation, they could create patterns of unprecedented complexity and beauty. Bridges of stars and gas would connect the two galaxies, visible as luminous arcs spanning the firmament. The tidal tails, enormous streams of stars violently ripped from both galaxies by gravitational forces, would extend across vast portions of the sky. These structures would be visible primarily in long-exposure photographs or with telescopes, but the brightest ones might be apparent to the naked eye as faint traces of starlight. The supernova rate would increase dramatically during the peaks of star formation. In the current Milky Way, naked-eye supernovae are rare, occurring perhaps once every few centuries on average. During the starburst phase of the merger, several visible supernovae might occur every single year. Some would reach magnitudes rivaling Venus or even the crescent moon, becoming dominant objects in the night sky for weeks before fading. The band of the Milky Way, that familiar feature that has been part of the night sky throughout all of human history, would gradually dissolve as the disk structure became disorganized. In the final stages of the merger, when Andromeda has adopted its final elliptical shape, there would no longer be a coherent band of starlight. Instead, stars would be distributed more uniformly in all directions, denser toward the galactic center, fainter toward the outskirts. The constellations, those figures that have guided navigators and captivated poets for millennia, would completely vanish. The random motions of the stars during the merger would disperse the familiar configurations. New patterns would emerge, but without the long-term stability of the current constellations. In an elliptical galaxy, where stars orbit in random directions, constellations would noticeably change on timescales of merely a few million years. For civilizations surviving the merger, the event would offer unprecedented opportunities for astronomical science. Observing a galactic collision from the inside would provide data that no observation of distant galaxies could ever match. The physics of star formation under extreme conditions, the dynamics of gas flows at speeds of hundreds of kilometers per second, the real-time evolution of stellar populations on timescales of millions of years, all of this would be directly observable. The gravitational waves from the merging central black holes, though imperceptible without extremely sensitive instruments, would be detectable with sufficiently advanced technology. This event, one of the most energetic in the history of the local group, would be a treasure trove of information about gravitational physics under extreme conditions. However, real dangers would also exist. Although the probability of a direct stellar encounter is small, it is not zero. A star, passing within, say, 1,000 astronomical units of the Sun, would significantly perturb the Oort cloud, the vast reservoir of comets that surrounds the solar system at distances of tens of thousands of astronomical units. Such a perturbation could send swarms of comets into the inner solar system, dramatically increasing the impact rate on terrestrial planets for millions of years after the encounter. An even closer encounter, within 100 astronomical units or less, could perturb the orbits of the outer planets. Neptune, Uranus, even Saturn and Jupiter might see their orbits altered. In the worst-case scenario, a planet could be ejected completely from the solar system, becoming a rogue planet. Alternatively, orbits could become more eccentric, causing the giant planets to pass closer to the Sun at perihelion, which could potentially destabilize the orbits of the inner terrestrial planets through gravitational resonances. The probability of such close encounters is small but not negligible. Studies suggest that perhaps 10 to 20% of stellar systems will experience some level of gravitational perturbation during a galactic merger. Most of these perturbations will be minor, altering orbits only slightly. But for the small percentage that experiences truly close encounters, the consequences could be dramatic. There is also the danger of radiation. During the peaks of star formation, the supernova rate will dramatically increase. Although space is vast, and the probability of a specific supernova occurring dangerously close is small, with increased supernova rates, the cumulative probability over millions of years becomes significant. A supernova within 30 light-years could bathe the Earth in sufficient radiation to damage the ozone layer and affect life on the surface. One within 10 light-years could be catastrophic. Gamma-ray bursts, though even rarer than supernovae, represent a potentially greater danger. These events, the most luminous in the universe, emit high-energy radiation jets that can cause significant damage to planets at distances of thousands of light-years if the jet is oriented directly toward them. During periods of intense star formation, the probability of gamma-ray bursts increases proportionally to the number of massive stars being formed. Despite all these potential dangers, the fundamental irony remains. These are dangers that Earth will almost certainly never face. Not because they are improbable, but because Earth will be dead long before they materialize. The evolution of the Sun, a predictable and relatively well-understood process, will seal our planet's fate billions of years before the galactic collision reaches its climax. This realization does not diminish the scientific importance or the cosmic magnificence of the Andromeda-Milky Way merger. It remains one of the most significant events in the future history of the local universe, a fundamental transformation of the structure of the local group. But it changes our relationship with the event. We are not destined participants who will witness this cosmic drama. We are transient observers who, by a chance of cosmological timing, exist in the pre-merger era, capable of predicting it but not of witnessing it. Perhaps this temporal perspective offers us a lesson in cosmic humility. The universe operates on timescales that completely transcend human existence, or even the existence of our planet. The events we consider immutable, such as the positions of galaxies in the sky, are actually momentary on cosmic scales. What appears permanent is transient. What appears distant is inevitable. And yet, facing our ultimate definitive fate as a planet orbiting a dying star, we must still ask, what will remain afterward? What form will Lactomida take once the merger is complete? And on the vast timescales of the deep future, what further transformations await? Part 5. Lactomeda, the future of the merged galaxy. After 7 billion years of unrelenting gravitational chaos, of repeated passes, of spiral arms torn and reformed, of spectacular starburst explosions that lit up intergalactic space with the light of millions of newborn suns, the final product at last emerges: Lactomeda. This new, colossal galaxy, born from the violent fusion of two major spiral giants, represents the culmination of one of the most fundamental processes in cosmic evolution: the merger of massive galaxies. Lactomeda will be a giant elliptical galaxy, fundamentally different in both structure and appearance from its progenitor galaxies. Where Andromeda and the Milky Way displayed elegant thin disks with sharply defined spiral arms, Lactomeda will exhibit a spheroidal or ovoid shape devoid of distinctive organized features. There will be no spiral arms, no thin, orderly rotating disk. Instead, approximately 1.4 trillion stars will orbit the galactic center on random, chaotic trajectories, moving in all directions without preference for any particular plane. The sheer size of Lactomeda will be considerable. Its effective radius, the distance from the center that contains half of the galaxy's total light, will likely be about 100,000 light-years, similar to the current size of the Milky Way. However, this comparison is misleading. Unlike spiral galaxies, where the majority of stars are confined to a thin disk, The stars in Lactomeda will be distributed throughout a massive three-dimensional volume. Lactomeda's stellar halo could extend 300,000 light-years or more from the center, with individual stars and residual stellar streams reaching even greater distances. Lactomeda's total luminosity will be the sum of its progenitors' luminosities, shining with the combined light of over 1 trillion suns. However, this light will be predominantly reddish or yellowish in color. The reason is simple. Following the intense episodes of star formation during the merger, the interstellar gas, the crucial fuel for new stars, will have been largely depleted or violently expelled. Without continuous star formation, the massive, brilliant blue stars, which live for only a few million years, will quickly disappear. Only the low and medium mass stars, which glow with red or yellow light and live for billions or even trillions of years, will remain. Lactomeda will be, in astronomical terminology, a red and dead galaxy. Star formation will have ceased almost entirely. The galaxy will evolve passively, slowly aging as its stars gradually consume their nuclear fuel. The galaxy's colors will progressively shift toward the red as even the medium-mass stars eventually die, leaving behind only the lowest mass red dwarf stars, objects so dim and long-lived that they can continue to shine for trillions of years. At the heart of Lactomeda will reside a single supermassive black hole, the product of the merger of the central black holes of Andromeda and the Milky Way. With a combined mass of approximately 110 million to 240 million solar masses, this gravitational monster will dominate the galaxy's nuclear region. Although currently quiescent compared to the black holes in violently active galactic nuclei, it could occasionally feed on unfortunate stars that venture too close, or on residual gas clouds, producing brief, powerful flares of high-energy radiation. The black hole merger, one of the most energetic events in the local group's history, will have occurred billions of years prior. The gravitational waves emitted during that spectacular event will have propagated through space at the speed of light, reaching galaxies billions of light-years away. For observers in those distant galaxies with sufficiently sensitive gravitational wave detectors, the event would have appeared as a characteristic chirp, a signal rapidly increasing in frequency and amplitude before abruptly cutting off, the unmistakable signature of two black holes fusing. The distribution of dark matter within Lactomeda will be crucial to its structure and dynamics, even though it is invisible to direct observation. The dark matter halo, resulting from the combination of the halos of Andromeda and the Milky Way, could extend up to 1 million light-years or more from the galactic center. This massive halo, containing perhaps 2 trillion solar masses or more of dark matter, will dominate the galaxy's gravity, determining the orbits of the visible stars and any surviving satellite galaxies. The minor satellite galaxies of the local group will have experienced varied fates. Some, like the Triangulum galaxy, will have been completely absorbed by Lactomeda, their stars dispersed and thoroughly mixed with the general population. Others, particularly the dwarf galaxies on very distant orbits, might survive as Lactomeda's satellites, continuing their journeys around this new galactic giant. A few may have been ejected completely during violent gravitational encounters, becoming rogue galaxies in intergalactic space. The average metallicity of the stars in Lactomeda will be higher than in the progenitor galaxies. The multiple generations of star formation, particularly the intense episodes during the merger, will have enriched the interstellar medium with heavy elements forged in the cores of massive stars and dispersed by supernovae. The last generations of stars formed before star formation ceased will contain significant abundances of carbon, oxygen, nitrogen, iron, and other elements crucial for complex chemistry and potentially for life. However, Lactomeda's future will not be one of eternal isolation. The galaxy will not exist in a vacuum. Other galaxies in the local universe will continue to evolve, and some will eventually interact with Lactomeda. The local group, the cluster of galaxies to which the Milky Way and Andromeda belong, contains over 80 known galaxies. Many of these are small dwarf galaxies that will eventually be absorbed by Lactomeda or ejected. But some more massive structures might persist. On truly immense timescales, tens of billions of years into the future, the accelerating expansion of the universe will play an increasingly important role. This expansion, driven by the mysterious dark energy, is gradually separating clusters of galaxies from one another. Galaxies within the local group will remain gravitationally bound, but neighboring galactic groups will recede faster and faster, eventually disappearing beyond the cosmological horizon. Within approximately 100 billion years from the present, the sky viewed from Lactomeda will be radically different from the current sky. Distant galaxies, those we now see with powerful telescopes, will have been carried so far away by the expansion of the universe that their light will no longer be able to reach us. The observable universe will have shrunk dramatically. For observers on Lactomeda at that remote epoch, assuming technological civilizations exist, the visible universe will consist essentially only of Lactomeda and any remnant satellite galaxies in the local group. This is a deeply unsettling prospect from a scientific standpoint. Astronomers of the far future, observing a universe that appears to consist only of their own galaxy surrounded by dark void, might reasonably conclude that they live in a static, eternal, and immutable universe. They would have no evidence of cosmic expansion, of the Big Bang, or of the existence of billions of other galaxies. The history of the universe, so painstakingly unraveled by 21st century astronomers, would be inaccessible to them. But even Lactomeda will not last forever. On timescales of trillions of years, subtle processes will begin to alter the galaxy. Low-mass stars, which can shine for trillions of years, will eventually exhaust their fuel and die, turning into cold white dwarfs. The galaxy will gradually darken as fewer and fewer stars remain active. Within 10 trillion years, perhaps only 1% of Lactomeda's original stars will still be shining. Gravitational encounters between stars, though rare, will occasionally occur even on timescales of trillions of years. Some of these encounters will impart enough energy to a star to completely eject it from the galaxy. Very gradually, over nearly inconceivable spans of time, Lactomeda could evaporate, losing stars one by one to intergalactic space. This process of galactic evaporation is extremely slow, requiring perhaps 10 to the power of 19 years or more, a number with 19 zeros, 1 million billion times the current age of the universe. Simultaneously, other processes will be at play. The stars that remain bound to the galaxy will gradually sink toward the center due to a process called dynamical friction. As stars gravitationally interact, some gain energy and move to more outward orbits, while others lose energy and fall inward. This process, acting over timescales of billions of years, will cause the galaxy to slowly contract, becoming denser at its center. In the very core of this contracted galaxy, the supermassive black hole will continue to grow slowly, accumulating stars and stellar remnants that venture too close. Eventually, on timescales of perhaps 10 to the power of 20 years, a significant fraction of the galaxy's mass might have been consumed by the central black hole, creating a black hole of billions or trillions of solar masses, surrounded by a faint halo of scattered stars and dark objects. But even black holes are not eternal. According to quantum physics, black holes slowly emit radiation, a process known as Hawking radiation. For massive black holes, this radiation is extraordinarily weak, but given enough time, it will eventually completely evaporate the black hole. For a 1 billion solar mass black hole, the time required for complete evaporation is approximately 10 to the power of 99 years, a number so vast that it utterly defies all comprehension. These timescales are so immense that they completely transcend any meaningful concept of the future. They are spans of time over which not only stars and planets, but the galaxies themselves, and perhaps the fundamental structures of matter, dissolve. They are spans of time over which the universe transforms into something completely alien to our current experience, perhaps a cold, dark vacuum populated only by scattered particles and faint background radiation. Returning to more accessible timescales, within the next 10 to 20 billion years, Andromeda will dominate the local group. Its gravity will govern the orbits of any remnant satellite galaxies. Its presence will define the structure of local space. For any civilization that might exist in that future, Andromeda will be the observable universe, the totality of what they can directly see and explore. The final irony is that this entire epic transformation, this merger of two giant galaxies that will take billions of years to complete, will yield a galaxy that is, in many respects, less interesting than its progenitors. Spiral galaxies, with their active star formation, their dynamic arms, their mix of young and old stars, are vibrant, evolutionarily active objects. Elliptical galaxies, in contrast, are largely passive, slowly evolving without dramatic events. However, from another perspective, Andromeda will represent a triumph of gravity, a demonstration of the universe's fundamental tendency toward hierarchical structure. Early stars formed from gas clouds, stars clustered into galaxies, galaxies merged to form larger galaxies. This process of hierarchical construction, driven by gravity acting over billions of years, is one of the central themes in the universe's history. Andromeda will stand as a testament to this process, an object that contains within its structure the complete history of its two progenitor galaxies. The oldest stars in Andromeda, those formed over 13 billion years ago in the earliest epochs of Andromeda and the Milky Way, will hold within their chemical composition information about conditions in the early universe. The youngest stars, formed during the merger, will preserve evidence of the dramatic episodes of collision-induced star formation. Stellar streams and substructures in the halo will trace the patterns of merger and galactic cannibalism that sculpted the galaxy. For astronomers of the far future, assuming they exist, Andromeda will be a fossil record, an archive of cosmic history stretching billions of years into the past. By carefully studying the stellar populations, the orbits, and the chemical compositions, they could reconstruct the history of the merger, identify which stars originally came from the Milky Way versus Andromeda, and trace the temporal sequence of events during the fusion. Facing the conclusion of our journey, we must step back and contemplate what we have learned. We have followed the story of Andromeda from its current position, a majestic spiral galaxy 2.5 million light-years away, through its inevitable collision with our own Milky Way, all the way to the final product, Andromeda, emerging billions of years in the future. We have explored the anatomy of a cosmic giant, examined the chronology of a galactic merger, contemplated the fate of our own planet, and glimpsed the deep future of the resulting galaxy. Throughout this journey, a recurring theme has been scale. The spatial scale, distances measured in millions of light-years, galaxies containing trillions of stars. The temporal scale, events unfolding over billions of years, processes operating on timeframes that exceed the existence of planets and stars. The energetic scale, black hole mergers releasing more energy in minutes than all the stars in the observable universe emit during the same period. These scales defy human comprehension. Our species has existed for only a few 100,000 years. Human civilization, only a few thousand years. Modern science, only a few centuries. Yet, In this briefest cosmic blink of time, we have developed the capacity to understand and predict events that will occur billions of years into the future, and to trace the history of the universe billions of years into the past. There is a profound beauty in this capability. We are, in the words of the astronomer Carl Sagan, cosmic matter that has begun to know itself. The atoms in our bodies were forged in the cores of stars that lived and died billions of years ago. We are literally made of stardust, and now, with our telescopes and instruments, we observe the stars that created us, predict the destiny of galaxies, and unravel the secrets of the cosmos. The merger between Andromeda and the Milky Way, this grandiose event we have explored in detail, will not directly affect us. Humanity, if it survives, will do so in forms we cannot currently imagine, perhaps scattered among the stars, perhaps transformed beyond recognition by technologies we have not yet conceived. Earth, our home, will be long dead before the merger reaches its culmination, a victim not of cosmic catastrophe, but of the natural life cycle of our sun. Nevertheless, the knowledge of this future event connects us to something larger than ourselves. It reminds us that we are part of a dynamic, evolving universe, a cosmos that changes and transforms on vast timescales. The galaxies we see in the night sky are not eternal and immutable. They are entities with histories, with futures, with destinies that we can predict, even if we cannot witness them. In the decades and centuries to come, our knowledge of Andromeda, of the predicted merger, and of Andromeda that will eventually emerge, will only improve. New telescopes will reveal ever finer details of Andromeda's structure. More sophisticated computer simulations will refine our predictions about the course of the merger. Perhaps we will even develop technologies that allow us to directly observe the early stages of the process, watching as Andromeda slowly grows in the sky over generations. But regardless of what future discoveries await us, the fundamental narrative will remain. Two giant galaxies, Andromeda and the Milky Way, are inexorably approaching one another, destined to merge in a gravitational embrace that will completely transform the structure of the local group. From their union will be born Andromeda, a new galaxy that will dominate the local universe for billions of years to come. This is a story of cosmic scale, of gravitational power, of inevitable transformation. It is a story that began billions of years ago when the first condensations of dark matter began to collapse, forming the seeds that would eventually become galaxies. It is a story that will continue for billions of years into the future, long after the last evidence of our civilization has vanished. And yet, for a brief moment in cosmic history, we are here to contemplate it, to understand it, and to marvel at the magnificence and inevitability of it all. In that sense, we are incredibly fortunate. We live in an era in which science has advanced enough to reveal these cosmic secrets to us, but not so far into the future that the events we predict have already occurred. We are witnesses to the before, capable of imagining the during, but destined to never see the after. Perhaps that is the final lesson of our exploration of Andromeda and its destiny. The universe operates on scales that completely transcend individual or even collective human experience. We are not the protagonists of this cosmic story. We are transient observers, lucky to be able to glimpse both the past and the future, but fundamentally limited by our mortality and the mortality of our planet. And yet, in that glimpse, in that understanding, we find something profoundly meaningful. Because even though we may not witness the merger of Andromeda and the Milky Way, even though Earth may be dead and the Sun extinguished when it occurs, the fact that we can predict it, understand it, and imagine it is, in itself, an extraordinary triumph of the human intellect and the spirit of exploration that defines our species. Andromeda will continue its journey toward us. The collision will occur. Andromeda will be born. And although no human eye will witness it, the event will unfold exactly as our simulations predict, a testament to the immutable laws of physics and the human capacity to comprehend them. In that comprehension, in that knowledge, resides a form of immortality. Although we, as individuals, as a civilization, even as a species, are transient, the truths we have uncovered about the cosmos will endure as long as the universe itself exists.